In this module, we shall discuss about infinite product. In previous module, we have already discussed about finite products. So, it is not difficult to define finite product. We can define without loss of generality, we can define finite products taking two sets. So, if we take two sets, by finite product we mean all ordered pairs taking first one from the first set and the second one from second set. Now, what happens if we take that arbitrary Cartesian product? Let us go to side presentation. So, now we will define arbitrary product of topological spaces. First, we have to define arbitrary Cartesian product of sets. For finite product, we have already told that we have considered just ordered pairs. So, now if we take countably infinitely many sets, so then their Cartesian product we can take in the form of sequences. That means, if Xn is a collection of countably infinitely many non-empty sets, then their Cartesian product can be considered as the all functions from the set of natural number to union of Xn such that n belongs to capital N, such that f of m belongs to Xm. So, why we have been able to define in this form? Because the set N is well ordered. Every subset of N has a first element. We have been able to define arbitrary product. But if we take arbitrary many non-empty sets, that means if we take a collection Xi such that I belongs to I, where I is an arbitrary set, then what will be the product? Let us first define in the same manner what we have discussed about countably infinitely many sets. We define the product as all x from I to union xi such that I belongs to capital I, where xi belongs to capital Xi. So, the question here is whether this product is at all non-empty. Axiom of choice precisely tells us that if all xi are non-empty, then product is non-empty. The idea behind it is that if we can make a set well ordered, then their Cartesian product will be non-empty. We have already observed in case of countably infinite product that as n is well ordered, we have been able to define countably infinitely product. So, if the index set for arbitrarily case can be well ordered, then here also we can define arbitrary product. Before going to finite product, let us observe the following fact for finitely many products. Let x1, x2, xn be finitely many topological spaces. Without loss of generality, we can consider two spaces, and let A be another topological spaces. Then a function f from A to product of xi is continuous if and only if pi I composition f is continuous for each I, where pi I is the ith projection map. For the proof, if f is continuous, it is clear that pi I composition f is continuous for each pi I. For the converse, let pi I composition f is continuous for each I, and let U be an open set in the product. Then there exists an open set Ui in each xi such that U is equal to product of Ui. In fact, we can work with the basic open sets. If we work with the basic open sets, then we can write it in this way, and we already know that there is no harm if we work with the basic open sets. So, F inverse product of ui is equal to all A belongs to capital A such that F A belongs to ui for all I. That means which is equal to F inverse intersection ui, intersection runs over from 1 to n. This is a very natural theorem for finite product. So, when we will generalize the finite product to arbitrary case, we should expect that this will hold for arbitrary case also. First, let us try to introduce the infinite product as in the case of finite product. Let us consider topological spaces xn such that n belongs to n. That means countably infinitely many topological spaces, and let script B is equal to all product of ui such that ui is open set in xi. Then it can be easily show that the collection script B is a basis for some topology. One might think to consider this collection as basis for infinite product, but this definition will not be a successful generalization of finite case to infinite case, which can be proved from the following example. Let us consider R with the usual topology and consider the topology constructed as above on Rn. That means taking all product of all basic open sets. Now consider the mapping f from R to Rn as f of x is equal to x x x like this. That means each component mapping are identity map, which are obviously continuous. If the above definition is a successful generalization of product topology, then the mapping f from R to Rn should be continuous as the finite case. But if we consider the open set U is equal to -1 to 1 open interval Cartesian product minus half to half Cartesian product dot dot Cartesian product minus 1 by n to 1 by n Cartesian product and so on, then F inverse U is equal to intersection n by n minus 1 by n to 1 by n, which is equal to 0, and we know that this is not open set, hence F is not continuous. So, in this way of definition we do not get any successful generalization of finite product topology. We have to think otherwise. Now we try to define infinite product in the following manner. If I is a non-empty set and for each small I in capital I we have a topological space capital Xi, then for each I belongs to capital I we define the following collection: script Si is equal to pi I inverse ui such that I belongs to capital I, and let us take script S is equal to union of script Si such that I belongs to capital I. So, what is pi I inverse script ui? So, pi I inverse script ui, if think as the Cartesian product, this is equal to a product, this is equal to a Cartesian product which is only equal with ui in the ith coordinate and except the ith coordinate everywhere, that is equal to xi. Now it is easy to observe that S is a subbasis for some topology on Xi, because if we take any point in the product of Xi, then we will get a member from script S which will continue that point. The topology generated by script S will be called product topology on product of Xi. If we view in the coordinate wise, a typical subbasis element will be of the form product of ui, where ui is equal to xi for all I except a single coordinate I. So, basis element of infinite product. What will be the figure of a typical basic open set for infinite product? We have already understand that a figure of a typical subbasis element will be as product of ui, where ui is equal to xi except for only one coordinate. Now, when we construct the basic open sets from subbasic open sets, we take all possible finite intersections. That means, we take intersection I belongs to F such that pi I inverse ui, where F is a finite subset of I. So, what we will get? We get a set of the form product of ui I belongs to I, where ui is equal to xi for all I except finitely many i's. As usual, taking basic open sets in the factor space in place of open sets also give rise to the product topology. So, we have discussed what is product topology. We have observed that from finite product to infinite product, the direct generalization is not so much effective. What we have shown by the example from f from r to r to the power omega defined by fx is equal to x. So, this misses the very natural property from a topological space to a product space. A mapping is continuous if and only if its composition with each projection map is continuous. But so, now we will check that whether this type of product, for this type of product, this result holds. Now, we are going to show that this definition of product topology is the successful generalization of the product topology which we have defined for finite product. Let us first state the following proposition which will be useful for our future purpose. Let xi such that I belongs to I, where I is an index set, be a collection of topological spaces, and let capital X be their product with the product topology as defined. Then projection map pi I from X onto xi is continuous and open. This can be proved very much easily just writing the basics open sets in the coordinate form. When we write basic open sets in the coordinate form, it becomes of the form its product of ui such that I belongs to I, where except finitely many all ui are whole equal to whole xi. In this connection, one can note that projection maps are not necessarily closed, though projection maps are necessarily open. This result about the closure will require for the next result. Let x a such that a belongs to I be a collection of topological spaces indexed by capital I, and let capital A is subset of x a for each a. Now, if x a is the product space, then product of closure of a is equal to the closure of product of A. That means closure behaves well under product, we can say in this way. For the proof, let us consider x is equal to xa such that A belongs to A in the product of AA bar, and let product of UA be a basis open set for the product topology which contains x. That means we have taken a basic open set of x. Here by bold x we have meant that that is an element of product. Now since x A belongs to A closure, for each small a belongs to capital I, we can choose a point y A belongs to UA intersection A. That means UA intersection A contains a point YA for each A. Then the point y is equal to YAA belongs to both U and product of AA. Therefore, x belongs to the closure of product of AA. For the converse, let x be a point in the product of AA closure. That means closure of product of AA. We claim that for any index A belongs to capital I, XA is in the closure of AA. For this we have to show that any neighborhood VB of XA in the capital XA topological space meets AA. So, let VB be an arbitrary open set of capital XB containing XB. Now, since pi b inverse VB is open in product of XA in the product topology, in fact this is a subbasic open set, it contains a point y in the product of AA. Then YB belongs to VB intersection AB. It follows that XB belongs to AB closure. The following theorem shows that product topology is the successful generalization of finite product topology, which we are trying to say that let X be a topological space and XA such that A belongs to I be a collection of topological space indexed by the set capital I. Again, let consider small f is a function from x to the product of XA given by fx is equal to fax A belongs to capital I, where each fa from x to xa is a function. Now, let product of xa have given the product topology, then the function f is continuous if and only if each fa is continuous. So, if we can prove this, we can say that this is the successful generalization of finite product topology. For the proof, let the given condition, that is f from x to product of xa be continuous. Then the function fb is in fact equal with the composition mapping pi b composition f. So, fb is the composition of two continuous functions small f and pi b, hence this is continuous. For the converse part, we have to prove that fb is continuous. But what is fb inverse ub, where ub is an open set in capital XB? This is nothing except f inverse of pi b inverse u b, but pi b is the projection map, so continuous, that means pi b inverse u b is an open set. Now since f is given as continuous, therefore f inverse of pi b inverse u b, that is also open set, hence f b inverse u b is an open set. This means that f b is continuous, and this is true for all each b belongs to capital I. So this shows that our theorem. Now we go slightly different discussion called weak topology. Let us first define what do we mean by weak topology. After that we will show that what we have defined as product topology, that is nothing except the weak topology generated by the projection mappings. Let capital X be a set and Xi be a topological spaces with Fi from X to Xi for each I belongs to capital I. Then the weak topology induced on X by the collection Fi is the smallest topology on X, making each Fi is continuous. Evidently, the topology on X for which the sets Fi inverse Gi for I belongs to I and Gi is open in Xi form a subbasis for some topology on X. Now let us consider the following proposition. Let Xi such that I belongs to capital I be a collection of topological spaces. If Z is a topological space and G from Z to X is a function, then G is continuous if and only if Fi compose G from Z to Xi is continuous for every I in capital I. Proof: if G is continuous, then Fi compose G is the composition of two continuous functions and is therefore continuous. Now assume each Fi compose G is continuous and let script W be the topology of Z. To show that G is continuous, we need only show that G inverse S belongs to W for S in script S, where script S is the topology on capital X. But if small I belongs to capital I and G belongs to tau I, where tau I is the topology on capital Xi, then G inverse composition Fi inverse is equal to Fi compose G whole inverse of G, and this belongs to script W since Fi compose G is continuous mapping. Now let us compare between weak topology and product topology. That means we wish to show the following theorem. The product topology is in fact the weak topology on product of Xi for which each projection map is continuous. The proof is easy very much. In fact, if tau is any topology on the product in which each projection map is continuous, then for each j, if Gj is open in Xj, then pi j inverse Gj belongs to tau. Consequently, the members of a subbasis for the product topology all belong to tau, and hence the product topology is contained in tau. We will prove a result that how subspace behaves for product topology. That means let us consider X alpha be a topological space and let A alpha be the subspaces of X alpha, then it is possible to induce topology on the product set A alpha in two ways. The first way is each A alpha is a topological space as a subspace of X alpha. So, product of A alpha is a topological space. And another thing is product of A alpha is a subset of product of X alpha. So, we can induce a topology on product of A alpha as a subspace from the product topology of product of X alpha. So, the question is whether these topology are equal or not. In the following theorem, we will show that these two topology are same. Let A alpha be a subspace of X alpha and consider the topological spaces A alpha and X alpha. Then product of A alpha is a subspace of product of X alpha. The proof is not difficult. In fact, let us consider a basic open set product of U alpha of product of A alpha. Here product of A alpha is considered as the topological space, product topological space of A alphas. Then there exist finitely many indices alpha 1, alpha 2, alpha k such that for all other alpha not equal to alpha 1, alpha 2, alpha k, we have U alpha is equal to A alpha. Since each A alpha is a subspace of A alpha, there exists open set O alpha in capital X alpha such that U alpha is equal to O alpha intersection A alpha for each alpha belongs to J. Let us consider the set product of O alpha, alpha belongs to J, where O alpha is equal to X alpha for all alpha belongs to J minus alpha 1, alpha 2, alpha k. Then we can see that product of O alpha intersection product of A alpha is equal to product of U alpha. This proves the result. Next, we will define a map called evaluation map which will be required for our future purpose. Let F alpha from X to product of X alpha be a collection of continuous maps. Then the evaluation map E from X to product of X alpha induced by the collection F alpha from X to product of X alpha is defined by E of X at the coordinate alpha is equal to F alpha X. F alpha from X to X alpha such that alpha belongs to I is said to separate points in capital X if whenever X not equal to Y in capital X, then for some alpha belongs to capital I, F alpha X not equal to F alpha Y. That means the collection F alpha is said to separate points if at least in some coordinate F alpha X and F alpha Y are different. We will use this in proving Eurytion's metrization theorem in future. With this, we conclude the discussion on product topology. And also with this discussion, we conclude the first chapter of this discussion on topology. In the next chapter, we will go to discuss different types of topological properties.